Hello everyone, today we're going to be talking about Hamilton paths and circuits. Okay, let's first talk about the definition. A Hamilton path is a path that visits each vertex of the graph exactly once. And a Hamilton circuit is a similar definition. It's a circuit that visits each vertex of the graph exactly once. And we should note here, you do not have to use every edge. Okay. All right. Let's compare Hamilton graphs and circuits, or Hamilton paths and circuits to Euler paths and circuits. Okay, so on Hamilton paths and circuits, are we allowed to repeat vertices? And the answer is no, you cannot repeat vertices. On an Euler path or circuit, yes, you're definitely allowed to repeat vertices. On a Hamilton path or circuit, do you have to use every edge? No, you do not have to use every edge. On an Euler one, yes, you do have to use every edge. And what's similar about them is you're not allowed to repeat edges on either one. Okay, so for Euler, it's about using all of the edges, and that's what we care about there. Hamilton, it's about using all of the vertices, each one only once, and that's what we care about in this section. And let's go ahead and do our first example. Okay, so part A, we just want to find one Hamilton circuit in this graph. So let's go ahead and find one that starts at A. Okay, so we could go from A to G. And then, let's see, we could go over to F. And then E. And C. And then let's go over to B. Down to D. And over to A. And let's keep in mind here, there's a bunch of edges that we haven't used, all of these edges that are left in black, but we don't care about using all the edges, we just want to hit every vertex. So there's one Hamilton circuit in this graph. All right. Now we want to find a Hamilton path that starts at A and ends at B. So instead, we still want to hit every vertex, but we want to start at A and end at B. All right. Well, maybe let's go A to D. And we're sort of just guessing and checking here, right? We just want to use edges that we've got and try to hit every vertex. All right. We don't want to go from here straight up to B, because we know that B has to be the last vertex and we're not allowed to repeat vertices. So if we're not going to go straight up, then we're going to go over to C. And let's see here. Let's go down to E, and let's make sure we're writing this down. A to D, D to C, C to E. And again, we don't want to repeat vertices, so we're not going to go up to B. We're going to go over to F. And the only vertices that we haven't hit are G and B. That means we can't take this edge from F up to A. We've got to go over to G. And then we've conveniently got an edge that goes from G to B. Okay, fantastic. So there is one Hamilton path that starts at A and ends at B. And that's not the only one. We could find another one. So let's go ahead and find another one. We could go from A down to G, over to F. F, we can go up to C, and then we don't want to go over to B because that one's going to be our last one. So we could go down to E, and then, ooh, this is not going to work actually, because our only options are to go up to B, which we can't do, or to go back to F, which we can't do either. So let's try going from F to E, and then up to C, and then we still need to hit D. We can take that edge down to D, and then take that edge straight up to B. So for many of these problems, there's not just one Hamilton path or Hamilton circuit. There are lots of different options. Okay, so part C, we want to find a Hamilton path that starts at D and ends at F. All right, so from D we have several options. Okay, we can go up to A, up to B, or up to C, and I am going to choose to go over to A. And now from A, we've got several options again. We can go down to G or over to B. Let's go over to B. And we can go over to C or down to E. Go down to E, and then we could go up to C, and now we can't go back to B, but we could go down to F, but there's a problem. We've ended our path, but we haven't yet hit G. So we've got to do another option. Okay, so we're still going to start at D. And let's go up to B this time. And we can take B over to C. We can take C down to E. Now we can't go to F, and again, we can't go up to B. That's a problem. Okay, so we're gonna start over again. And you can see that it really does take a little bit of work to kind of figure out how you've got a Hamilton path or circuit. So let's go straight over to C, and let's go down to E. And now we haven't hit B yet, so we don't have the problem of repeating B, so we can go up to B, and we already hit D, so our options to go over to A, and now we can go down to G, and over to F. So we've got this Hamilton path that starts at D and traces out all the way around the graph to F. Does not use every edge, but does hit every vertex. In our next example, we want to answer a couple questions about this graph here. First question is, why does this graph contain no Hamilton circuits? Okay. So let's talk about this. If we were to try to find one, say we wanted to find one that started and ended at F, well, we could go up to A, down to B, and then we have an issue, right? We have to hit C and D, and we have to hit E, but we're not allowed to repeat vertices. So from B, if we go up to hit C, well, we can't come back through to get to this other side of the graph. And similarly, if from B we go down to E, there's no way for us to get back to hit the vertices on this other side of the graph. So let's write that out. Okay. It contains no Hamilton circuits, okay? To complete a circuit, that hits every vertex, we would have to pass through B twice. And in a Hamilton circuit, you're not allowed to repeat vertices. All right, so no Hamilton circuits, but why does it have a Hamilton path? Okay, let's talk about this. So if we thought about a path starting at F, we could go up to A, down to B, and either over to E or over to C, but again, we run into the same problem. We're gonna have to pass through B twice. So our path isn't gonna start at F, but let's try starting at A. Then we can hit all of the vertices on the left side of the graph before we go through B. Then we can hit all the vertices on the right side of the graph. And because it's a path, we don't have to go back over to get to A. Okay, so because it's a path, we don't have to return through B to get back to the start. We can visit all vertices on one side of the graph, on one side of the graph before passing through B, which is sort of that point of no return. And then the path would end on the other side of B.